yours. Yeah, it's really annoying actually.
Okay, so let's get started then.
Okay. Yeah,
So,
let's get started. Yeah.
I'm using my computer here for the microphone. So I guess if some student has a question, I have to come here, unmute, and go back over there.
Sure.
Maybe I can leave
Really
unmuted.
annoying, actually.
Okay. Or I can leave the computer unmuted. Both work. I don't know what's better.
I don't know. That's your choice, but I think definitely call the person.
Yeah, Jisung is calling.
Because this is not sustainable for this sort of presentation.
Yes.
And they should fix that room. Basically, it's a bit unreasonable that that room is like that. Okay. Anyway, let's get started. It's such an easy fix, right? Rebooting the system every time doesn't make sense, especially the system is locked up. If we could reboot it, then that's perfectly fine. But
yeah,
they lock up the system so that
we cannot do anything.
I guess, yeah, we don't steal it or something.
Yeah. Okay. So I'm going to leave it unmuted. If it's annoying, you'd let me know. I can mute it later on.
Yeah. Okay. Okay. So I guess hello everyone. I don't see you, but I think there are a lot of people in the room. So what we're going to do today is, since many of you requested topics on virtual memory, rethinking virtual memory, I've asked two of my PhD students to present. Actually, one of them is not a PhD student anymore, Nastaran. She finished her PhD thesis last year, and she's still doing research on this topic. So her thesis was on, part of her thesis was on virtual memory frameworks that are fundamentally different from today. So she's going to present the virtual block interface. And then in the second part, Ataberk will present something related but different. So if that sounds good to everyone, let's get started. Nastran, thanks for doing this. You're, I think, 9 hours earlier than us, but hopefully it's still good.
Yeah, thank you for the introduction, Onur. It's my pleasure to be here today and present my work. So let me share the screen. I hope I have permissions to do that. I guess someone...
You are a co-host.
Yeah, but it says one participant can share at a time, so I guess... Oh, okay. I think it works. I think I figured it out. Okay, just a sec. Well, I forgot to change my background. So yes, this is my son. But okay, you guys see my first slide, right?
Yes, it looks good. I assume people in the room can hear Nastran, right? If there are any issues, Geraldo, let us know and we need to fix it. But we're assuming that people can, so go ahead.
Sounds good. Okay, let me just make sure that my cursor, okay. Yeah, so as I said, it is my pleasure to be here and present my work to you guys. I'm looking forward to a fruitful discussion after this presentation. And as Onur said, the presentation would be about rethinking the virtual memory. This is a direction that I have been pursuing for a while now. And before I begin, I would like to give you a little bit of information about where the motivation for the research that I'm going to present today and our other related projects on novel virtual memory frameworks come from. So as you guys know, modern computing systems heavily depend on the virtual memory to provide with many features that are, all of them are integral to the overall performance of the system as well as its functionality. But the problem is that virtual memory is facing some challenges today, critical challenges today, that makes it difficult to efficiently maintain this important component as it is in the system, and puts it as at a risk to keep it as it is. So this is the case mainly because of the fact that virtual memory was originally designed around 60 years ago, without having the diversity and the complexity of today's computing systems in mind. As a result of that, while the core concepts of virtual memory have remained mainly untouched, concepts that were developed decades ago, the nature and the characteristics of the other components of the system have changed significantly over the years. For example, the behavior and the nature of the workloads, the requirements, and also the architecture of different components in the system. So this mismatch between the existing virtual memory design and the other components of the system that are continuously evolving and diversifying has led to virtual memory officially becoming a performance bottleneck in modern computing systems. Efficiently and also quickly addressing this problem is increasingly important as the complexity and diversity of the computing systems is increasing every day. So the importance of this problem is acknowledged by both academia and industry. So we're not the only ones noticing this, which is kind of a good sign. And the importance of this problem for our community is evident considering the wide body of research and innovation that is designed to basically alleviate the overheads of the conventional virtual memory design when it is trying to adapt to the diversity in modern computing systems and also workloads that we see today. So now let me tell you why, despite all these prior works, we believe that there's still a long way to go, or in other words, what has been the motivation for our research in this direction, which I'm going to present part of it today. So the prior works built extensive optimizations and adjustments within the existing virtual memory design. But the problem is that no prior work actually considers fundamentally rethinking and redesigning the virtual memory from the ground up to make it more suitable for today's computing systems and also workloads' actual needs. So as you can guess now, our motivation in this direction of research has been to the fact that the optimizations and adjustments to the conventional virtual memory framework are not enough in making it suitable for our needs today. So we believe that a holistic solution is required to rethink and redesign the virtual memory from the ground up to make it work actually for today's system and even for future computing systems and workloads. So this work that I'm going to present today is our first step towards this direction. It is called the Virtual Block Interface. This was published in ISCA 2020. And yeah, so let's get started. I will start by giving you a high-level summary of the talk. So the motivation of this work, as I briefly told you, is that modern computing systems continue to diversify with respect to system architectures, emerging memory technologies, and also applications memory needs. Unfortunately, continually adapting the conventional virtual memory framework to each possible system configuration is challenging and often results in performance loss or requires non-trivial workarounds. Accordingly, our goal in this work was to design an alternative virtual memory framework that efficiently supports a wide variety of new system configurations and also provides the key features of the conventional virtual memory framework while eliminating its key inefficiencies. To this end, we propose virtual block interface in this work, a novel alternative virtual memory framework that delegates the physical memory management to a dedicated hardware in the memory controller. Vbi efficiently adapts to different and increasingly diverse system configurations. It also reduces the overheads and complexities related to the conventional virtual memory framework. In Vbi leads to many benefits that some are not really easily attainable in existing virtual memory framework. For example, low overhead page walks in virtualized environments or inherently virtual caches. We demonstrate the benefits of Vbi with two example use cases in this paper. The first one is that we experimented show that VBI significantly execution respectively. And second, we show that VBI significantly improves the effectiveness of heterogeneous main memory architectures. Here's the outline for my talk today, and I will first discuss our motivations a bit further. So as I said, and you guys all probably know, virtual memory is a core component of modern computing systems. The virtual memory model, however, has remained mainly the same since it was introduced. The conventional virtual memory model was originally designed for systems whose memory hierarchy fits a simple two-level model of a large but slow external storage. In such a configuration, the OS can easily abstract away the underlying memory architecture details and present applications with a unified view of memory. However, modern computing systems no longer follow this simple model and continue to diversify significantly. For example, with respect to emerging memory technologies and architectures, new system designs, and diverse memory requirements of modern applications. As a result, the OS must now efficiently meet the wide range of application memory requirements and leverage the advantages offered by emerging memory architectures and new system designs, while simultaneously hiding their complexities from the application. Unfortunately, this is a difficult problem to tackle in a generalized manner and results in virtual memory not being able to efficiently adapt to increasingly diverse system configurations. As a result, continuing to adapt the conventional virtual memory framework to today's diverse system configuration is challenging. Before diving into these challenges, let's start by taking a look at the conventional virtual memory design. So this figure shows the virtual memory management in Intel x86 as an example of a conventional virtual memory framework. In such a framework, each process is mapped to a single private virtual address space of fixed size, for example, 256 terabytes in Intel x86. The operating system controls the access permissions by managing the one-to-one mapping of processes to their associated virtual address space. And the OS defines the mapping from each process's virtual address space to the physical memory and stores both the mapping information as well as the permission information in a set of per-process page tables. The page tables are managed by the operating system, and they are read by the memory management unit in the processor to perform address translation. This design suffers from many fundamental challenges when adapting to the diversity and complexity of computing systems. Here, the first example is related to the.
Can you hear me?
Sorry?
So you're breaking up sometimes. Is it because of your connection or?
Oh, I don't know. My connection is supposed to be good here.
Okay, I don't know what it is then, but.
Is it bad?
Yeah, this is the multiple.
Is it too bad?
It's happened multiple times where you broke up and it became hard to follow. If there's something you can do on your end, please do. Otherwise, I guess we'll have to tolerate it.
Okay, let me think. I don't think this is the first time that this is happening. I don't think there's anything that they can change, actually.
Okay. It's not related to earphones, I assume, right? You're not using them.
No, I'm not. I'm using the mic on my laptop.
Okay. Yeah, let's continue, I think. I mean, it's not terrible, but
I can't. Is it only my voice or my connection that is breaking up?
It's your voice, basically. When you're transitioning, when you're clicking on things, sometimes your voice breaks up and we don't fully understand the sentence.
Okay, let me check using another microphone. Just a sec. I can use, I'm not sure that that one is better, but I can try. Does it make a difference?
Your voice is coming from deeper, but I think we'll have to try it.
Okay, let's continue like this and see if it helps.
Okay.
Yeah. So as I said, the first example of the challenges that the conventional virtual memory framework faces when adapting to the diversity and complexity of today's system is related to the inflexibility of the conventional virtual memory framework in adapting to the memory requirements of modern applications. And okay, yeah. Prior works show that applications can reduce the address translation overhead using flexible page tables that are customized to the application's actual memory footprint and access pattern. For example, using larger granularities based on the density of the allocated data. However, as I mentioned earlier, in conventional virtual memory frameworks, while the OS defines the virtual to physical address mapping in the page tables, the hardware must be able to read these tables to perform address translation. So this arrangement requires using rigid address translation structures that are shared between and also understood by both the hardware and the OS. For example, the 4-level page table of fixed granularity in Intel x86. As a result of the rigidity of the conventional virtual memory framework, it is challenging to implement the page table flexibility that applications can benefit from. Another example challenge exists when adapting the conventional virtual memory framework to virtualized environments. In virtualized environments, the guest OS is running on top of the host OS in a virtual machine. In such a setting, the guest OS is unaware that it is running in a virtual machine. As a result, it performs memory management on the emulated physical memory and translates the guest virtual address to the guest physical address, which is in fact the host virtual address. So the host OS then performs a second round of memory management and maps the host virtual address to the host physical address. This extra level of indirection results in many important issues, including the famous 2-dimensional page walk problem, where the number of memory accesses required to perform address translation increases dramatically. This issue makes it challenging to perform computation in virtualized environments. As you can imagine, it makes it challenging to perform computation efficiently. The third challenge that I discuss here happens when managing heterogeneous memory architectures. Enhancing performance with heterogeneous memories first requires dynamically mapping data to different physical memory regions according to the application requirements. For example, mapping frequently accessed data to the fast memory, as you can see in this figure. And also second, it needs a migration of the data when those requirements change. Since in conventional virtual memory framework, the OS defines and manages the address mapping, efficiently implementing such functionality faces the fundamental. Yeah,
can you stop just for a second for us to fix the audio here in the room? Someone just came by.
Okay.
Okay, good, thank you. Sorry, just sorry to interrupt.
Okay. So you want to...
Geraldo, I think they need to restart the machine. Something is wrong with that machine over there. This room is basically broken. I've had this issue N times. I guess they cannot hear us now.
Yeah, I guess so.
Yeah.
But did the quality of my voice got better, or is it still breaking up?
So your voice is coming from deeper. So overall quality. So basically, you weren't breaking up. That's the good part.
We're not breaking up? Okay, that's
Yeah,
good.
but the clarity became a bit worse in the sense that your voice was more powerful. So the earlier microphone was better, but somehow it was breaking up.
Yeah, I'll try to be louder. Maybe that helps.
Yeah, maybe. I know if they fix this issue. Yeah, we really need to change this room, Mohammed. I sent you an email. I think it doesn't really make sense to continue with such a room that's flaky. And they fundamentally need to fix the problem as opposed to trying to patch it every single time we have a lecture over here.
Yeah, I agree. I just replied to the email. I think there are a few things that we can do.
Yeah. Yeah, but I don't think we should tolerate it because it's very unreasonable. This is such a simple thing to fix.
Yeah.
Eins, zwei, drei. It's now.
And the other one. Oh, nice.
Yeah. Eins, zwei, drei, test. Yeah, yeah. Yeah. No, it doesn't help here. The problem is the device here. So if you want to take a look, there is this Vbi LAN. There you have, I think it's a little bit difficult to you.
Can you hear us, Onur?
Yes.
Okay, so I think here is fixed. Let me turn on the camera again.
So what was
And
the
I think you can start.
So what was the issue, Geraldo?
They need to reboot the system.
Yeah.
They need to go back to.
Yeah, Nastran, I think you can continue.
Okay, does this sound better?
Yeah, it's very good actually.
Okay, good, good. The old headphones work better, apparently. Okay, I'll go back to the beginning of us looking at this challenge.
But I think we can hear it touching some place. There's a lot of static. Maybe you can go back to the first microphone and we can try it again.
Is this better, Onur?
Yeah, this is better.
Okay. Let me know if it's if I need to switch back to my previous mic.
Okay.
Okay, so as I was saying, this is the third challenge that we're looking at, and it happens in heterogeneous memory architectures. So as I said, enhancing performance with heterogeneous memories first requires dynamically mapping information. Sorry, dynamically mapping data to different physical memory regions according to the application requirements. For example, as you can see in this figure, by mapping frequently accessed data to the fast region of the memory. And also it needs to migrate data once the requirements change. Since in conventional virtual memory framework, the OS defines and manages the address mapping, efficiently implementing such functionality faces the fundamental issue that the OS has low visibility into fine-grained runtime memory behavior information. As a result, it becomes challenging to make timely migration decisions based on quickly changing memory access pattern or other dynamic behavior in the system. So considering the key role that virtual memory has in the overall performance of the computing systems, a wide body of research, as I said, proposed mechanisms to alleviate the overheads that are associated with it. But the problem is that despite notable improvement that these prior works show, The problem is that they suffer from two major shortcomings. The first one is that they are mainly designed based on a specific system or workload characteristic, and as a result are applicable to only a limited set of problems or applications. And also second problem is that each solution requires a specialized and not necessarily compatible changes to both the operating system and the hardware, which makes implementing these proposals at the same time in one system a daunting prospect. This highlights the need for a holistic solution to efficiently support today's diverse system configurations. In response to the need for a holistic solution, our goal in this work was to design an alternative virtual memory framework that has two properties. First, to efficiently and flexibly support the increasingly diverse system configurations, and second, to provide the key features of the conventional virtual memory framework while eliminating its key inefficiencies. I will now describe the key idea and the guiding principles that VBI framework is built around. Considering the challenges that the operating system managed physical memory faces and the conventional virtual memory that we just looked at, the key idea in VBI is to delegate the physical memory management to a dedicated hardware in the memory controller. To this end, the VBI design is driven by three key guiding principles. The first one is that programs should be allowed to choose the size of their virtual address space. So this mitigates the high address translation overhead associated with unnecessarily large and also fixed size virtual address spaces in current virtual memory frameworks. The second one is that address translation should be decoupled from memory protection as they are logically separate. This enables opportunities to remove address translation from the critical path of an access protection check and to defer the address translation until the physical memory needs to be accessed, which results in lowering the overall overheads of virtual memory. It also enables the flexibility of managing address translation and access protection using separate structures, which are customized to their specific characteristics. The third guiding principle is that software should be allowed to communicate semantic information about the application data to the hardware. As shown by prior work, conveying data semantics to the hardware helps hardware to manage the underlying resources more intelligently. These three principles address the rigidness and the lack of information that is present in existing virtual memory framework and enables the reduction of its large overheads in today's systems. I will now describe an overview of VBI and how these three principles are implemented. This figure shows an overview of the VBI design compared to the conventional virtual memory framework. And now I will describe how VBI enables its key idea. VBI introduces a globally visible address space called the Vbi address space, which consists of a large set of virtual blocks of different sizes from a set of predefined size classes, which here you see an example of a set of size classes that we considered in the paper. All the virtual blocks are visible to all processes running on the system, and processes map each semantically meaningful unit of information, let's say a data structure or a shared library code, to a separate virtual block of the appropriate size. The globally visible VBI address space provides VBI with system-wide unique addresses called VBI addresses. And since they're globally unique, the VBI addresses can be directly used to access unchipped caches without requiring address translation. This enables inherently virtual caches seamlessly because there's no possibility of synonyms and homonyms since every address is unique system-wide. So accessing caches using the unique virtual VBI address enables our key idea by providing VBI with the ability to defer the address translation and memory allocation until it is necessary to access the physical memory. To this end, address translation and physical memory allocation duties are delegated to the hardware-based memory translation layer in the memory controller. So this enables many benefits, such as allocation of physical memory only when the location is truly needed to write data to the memory. It also avoids the two-dimensional page walks in virtual machines, as now the memory translation layer is the only component in the system that performs address translation. And finally, it helps enabling flexible translation structures, as they now can be separate from the structures that maintain the access permission information. So accordingly, in VBI, the OS no longer needs to manage address translation and memory allocation. Instead, it retains full control over access protection by controlling which programs have permission to access which virtual blocks. In order to access a virtual block, a process needs to be attached to that virtual block with correct permissions. To this end, the OS attaches the processes to the requested virtual blocks and stores the list of the virtual blocks attached to each process and their associated permissions in a per process table. Access protection is performed in the process, in the processor using this table.
Nasran,
yeah.
sorry for interrupting, but the same problem is happening now.
What is the problem with the audio?
Sorry.
It's been fine on my side. I'm not sure.
Yeah, so now we are using notebooks, microphone and speaker.
Okay. Should I switch back to my previous mic? Is that the issue?
No, the issue is this room.
Oh, okay. Do you want me to change your room?
We are trying to. The guy at least left the door open so we can reboot the thing ourselves.
Yeah, this is what happens when a problem is not fundamentally fixed, right?
It's a patch. It's going to keep happening every 15 minutes.
Yeah.
This is exactly what's happening with all the adjustments and optimizations in virtual memory.
Yeah.
Fundamental enough to fix it for once and all.
Yeah, except I think this issue with the room is easier to fix than virtual memory.
Agreed.
Maybe we have to carry our own speakers everywhere.
Yeah, that's a solution. Yeah, Mohammed, we need to change this room. There's no alternative option I see, because we're going to have a lot of presentations by students and we cannot afford this sort of, let's say.
Yeah, I'm sending the request.
Yeah. Either fix the problem for good or change the room, basically. There's no other option here.
I think the guy said the system is broken. I think we need to change it.
Yeah, if something is broken, it should be fixed, right?
Can you hear us, Onur? Yeah, I think we are fixed.
Yeah, I can hear you. Yeah, people on YouTube say it's fine. Yes, this is a problem not with the online infrastructure. It's a problem with the hard infrastructure in a room. Okay, shall Nastran continue then?
Yes, Nasran, you can go ahead.
Sounds good. Okay, so yeah, as I was saying, the way that it works is that for processes to have access to the virtual blocks, the OS attaches the processes to the requested virtual blocks and stores the list of the virtual blocks attached to each process and their associated permissions in a per process table. Access protection is performed in the processor using this table to ensure that the process has enough permissions to access the requested virtual block. In contrast to the conventional virtual memory framework, where each process is mapped to a single fixed size virtual address space, irrespective of its actual memory requirements, in VBI, any process can attach to any virtual block. Accordingly, the process's total virtual address space is defined by the set of virtual blocks that it actually needs and it is attached to. As a result, the address space size of each process is defined by its actual memory needs, which satisfies our first guiding principle, which was appropriately sized virtual address space for processes. Also, in contrast to the conventional design where the OS manages both the access permissions and the address mapping, Vbi decouples the two by delegating the address mapping to the memory translation layer while allowing the OS to retain full control over managing the access protections, which addresses our second guiding principle, which was decoupling address translation from access protection. Decoupling address translation and access protection allows Vbi to relax the constraint of sharing address translation structures with the OS, which exists in the conventional framework. And as a result, Vbi can maintain address translation information in a separate structure than access permission information. So this provides Vbi with the flexibility to employ different types of translation structures that are customized to the application's memory needs. And as a result of that, Vbi maintains a separate translation structure for each virtual block and customizes that address translation structure to suit the properties of the virtual block and the data that the virtual block is actually containing. So for example, single level tables for a small virtual block is an example of customizing the address translation structure to the memory requirements of the data. The flexibility of customizing the address translation structure to the virtual block's need lowers the address translation overhead in Vbi. In Vbi, each virtual block is associated with a set of information, including a bit vector that indicates the semantic and access properties of the virtual block's content, such as access pattern or latency and bandwidth requirements of the data. The properties bit vector enables Vbi to implement the third guiding principle by communicating the memory requirements and semantics of the data that the virtual block contains to the hardware. In our paper, you will find more information about what I just explained, including a detailed reference implementation and microarchitecture of Vbi. So I invite you guys to take a look at the paper and let me know if you have any questions or any ideas that we can discuss further. So now let's take a look at the optimizations that Vbi Design enables. Vbi naturally enables a variety of important optimizations which are not easily attainable in the conventional virtual memory framework. We discussed 7 examples of such optimizations in our paper. 3 of these optimizations are achieved using our guiding principles. I will explain 3 other examples of such optimizations in this presentation, and also I invite you to refer to our paper to read about another example of optimization that Vbi enables. Now let's take a look at the first example optimizations, which is inherently virtual caches. So as you guys know, a common approach to caches in the conventional framework is virtually indexed physically tagged caches. In this approach, the core issues a virtual address to the cache while the physical address is retrieved by accessing the TLB in parallel. So in case of a TLB hit, the physical address is issued to perform the tag lookup. And in case of a TLB miss, a page walk is needed to retrieve the physical address that is required to read the cache. In order to remove the overhead of address translation for cache accesses, virtually indexed, virtually tagged caches access the cache using virtual addresses without requiring the address translation. So the address translation is performed only prior to accessing physical memory in such a design. And as a result, virtually indexed, virtually tagged caches or VIVT caches reduce the address translation overhead by reducing the number of requests for address translation. But the problem is that most modern systems do not use VIVT caches because of 2 main issues. So the first one is that because virtual addresses are not globally unique in conventional systems, VIVT caches suffer from synonyms and homonyms, which require complex mechanisms to be handled. And second problem is that although address translation is not required to access VIVT caches, the access permission check required prior to access the cache access still necessitates accessing the TLB and can induce a page table walk on a TLB miss. This is because of the fact that the protection bits are stored as part of the page table entry for each page in current systems. So Vbi addresses both these issues. First, it accesses all on-chip caches using Vbi addresses. However, since these addresses are unique system-wide, VBI eliminates the possibility of synonyms and homonyms. And second, by decoupling access protection from address translation, VBI stores the protection and address translation information in separate sets of tables, which avoid the need to access translation structures for protection purposes. Therefore, VBI reduces the address translation overhead by naturally enabling benefits similar to VIVT caches without their known complications in current systems. Let's take a look at the second optimization example, which is called delayed physical memory allocation. So as I mentioned earlier, in virtually indexed physically tagged caches, the physical address is required to access the cache, which needs the data to be already mapped and allocated in the physical memory. On a cache miss, then, the actual cache line is looked up and returned to the cache. And in VBI, in contrast, all on-chip caches are inherently virtual and are directly accessed using the system-wide unique VBI addresses without requiring address translation. Therefore, the physical address is not needed to access the cache, and as a result, the cache line does not need to be mapped and allocated in the physical memory prior to being accessed in the cache. VBI exploits this opportunity and delays the allocation of physical memory for virtual blocks until it is necessary to access the physical memory. Accordingly, on a cache miss, if memory translation layer realizes that there's no memory allocated for the requested cache line, it simply returns a zeroed cache line. In this mechanism, the memory allocation for the virtual block happens when the first 30 cache line of that virtual block is written back to the physical memory. On the write back, the memory translation layer defines the VBI address to physical address mapping for the virtual block and allocates the virtual block in the physical memory. The delayed physical memory allocation provides VBI with many benefits that are not easily possible in the conventional virtual memory framework. The first one is that it eliminates the address translation for accesses to the regions that are not yet allocated, which reduces the address translation overhead of the system. And the second one is that it eliminates the original memory request from accessing the memory, as well as returning, because it returns a zero cache line, for accesses to the regions with no memory allocation, which results in improving the overall system performance by reducing the number of accesses to the physical memory. And finally, it avoids allocating memory for smaller virtual blocks that may never leave the cache during their lifetime, which reduces the memory footprint of the process. Can I continue, or is there any issues? Okay, I continue. As a result, by enabling delayed physical memory allocation, VBI reduces the address translation overhead, improves the overall system performance, and also reduces the total memory consumption of the process. Let's take a look at the third challenge, optimization that VBI enables, hopefully no challenges, which is eliminating the two-dimensional page walks in virtual machines, which I mentioned earlier. So as I mentioned, the conventional virtual memory framework suffers from two-dimensional page walks in virtual machines, where both the guest OS and the host OS perform address mapping. VBI, however, resolves this issue by the fact that in VBI, the guest and the host OS interact once to attach the process running on the virtual machine to its virtual blocks. And once attached, any memory access from the virtual machine directly uses a VBI address to access the cache. And since in VBI, the memory translation layer is the only component system-wide that manages address mapping, the address translation is performed only at the memory translation layer in the memory controller. As a result, unlike existing systems, address translation for virtual machine under VBI is no different from that for host. As a result, by eliminating the two-dimensional page walks, VBI reduces address translation overhead in virtualized environments. I will next discuss the methodology that we use for testing VBI and also evaluating our mechanism and the optimizations that I just mentioned. So we evaluated VBI using a heavily customized version of Ramulator to faithfully model all components of the memory subsystem, including the TLBs and the page tables. Our workloads, as you can see here, consist of benchmarks from Spec 2006, Spec 2017, Tailbench, and Graph 500. And here you can see a summary of the main parameters of our simulations. Let's take a look at the evaluation results. We evaluate VBI for two important use cases. In the first use case, we evaluate the impact of VBI on reducing the address translation overhead in both native execution and virtual machines. And here I present results for 3 baselines and 1 VBI configuration. So the baseline that we present here are baselines are native, where applications run natively on an Intel x86 system. Virtual, where applications run inside the virtual machine, and perfect TLB, which is an unrealistic version of native with no address translation overhead. We also show results for VBI full, which is VBI with all 7 optimizations that I mentioned earlier. You can see our paper for more system configurations and also more evaluations on those system configurations. So this figure compares the performance of virtual, VBI full, and perfect TLB systems normalized to the native. From this picture, we can make 5 observations. The first one is that we observe that virtual reduces the performance to 0.7 times on average compared to native. This is because of the fact that the 2-dimensional page table walk issue that was present in conventional virtual memory framework in virtualized environments is actually causing this performance loss. Second, we observed that perfect TLB improves the performance compared to native by 1.9 times on average, which is due to the removing the address translation overhead completely. And third, we observed that VBI full improves the performance by 2.4 times on average compared to native. And this is achieved through enabling all 7 optimizations that we mentioned earlier. Fourth observation is that VBI full improves the performance by 4.3 times on average compared to virtual. This is basically because of the fact that in contrast to the conventional frameworks, in VBI, the address translation overhead for the processes running inside a virtual machine is no different than the processes running natively on the system. As a result of that, VBI enables significant performance improvements in virtualized environments, which is not attainable with the conventional virtual memory framework. So the fifth observation is that VBI outperforms perfect TLB system by 49% on average. This is because the benefits of VBI and the optimizations that it enables is not limited to only reducing the address translation overhead. If you remember the delayed physical memory allocation that I mentioned earlier, as one of the optimizations that VBI enables, improves the overall system performance by reducing the traffic of the program memory accesses to the main memory. So we conclude that VBI can significantly improve performance in both native execution and virtual machines. As a second use case, we evaluate the benefits of VBI, the benefits that VBI offers in harnessing the full potentials of heterogeneous memory architectures. To this end, we evaluate VBI in a system with a hybrid PCM DRAM main memory architecture. And we examine 2 baseline systems. The first one is hotness on-ever PCM DRAM, where the mapping mechanism is on-ever of the data hotness, or basically access frequency. And the second one is ideal, which is an unrealistically perfect mapping mechanism that uses Oracle knowledge to always map frequently access data to the DRAM as the fast memory. We also evaluate a VBI configuration called Vbi PCM DRAM, where VBI maps and migrates frequently accessed virtual blocks to the DRAM. This figure compares the performance of VBI PCM DRAM and ideal normalized to the hotness on-ever PCM DRAM. So we observed that VBI PCM DRAM improves performance by 33% on average compared to the hotness on-ever PCM DRAM by accurately mapping and migrating the frequently accessed virtual blocks to the low latency DRAM. We observe similar benefits when using VBI in a system with tiered latency DRAM, which is another heterogeneous memory architecture. You guys can see those results in the paper. We conclude that VBI enables efficient data mapping and migration for heterogeneous memory systems. I will now conclude my talk. So in this work, we introduced the virtual block interface, a new virtual memory framework to address the challenges in adapting conventional virtual memory to today's increasingly diverse system configurations and workloads. The key idea of VBI is to delegate the physical memory management to a dedicated hardware in the memory controller. And the memory controller-based memory management in VBI enables many benefits that are not easily possible in existing virtual memory frameworks, such as inherently virtual caches or delayed physical memory allocation, and also avoiding two-dimensional page walks in virtual machines. We experimentally show that VBI significantly improves performance in both native execution and virtual machines and increases the effectiveness of managing heterogeneous main memory architectures. We conclude that VBI is a promising new virtual memory framework that can enable several important optimizations and increase the design flexibility for virtual memory. We believe and also hope that VBI will open up a new direction and many opportunities for future work in novel virtual memory frameworks. This was a quick presentation for the virtual block interface paper that we had in ISCA 2020, and I appreciate your attention and would be glad to have your questions, answer your questions.
Hey, thanks, Nastran. If there are questions, I think people in the room or Zoom, they can ask them. We took a little bit longer because of these technical issues, unfortunately.
Yeah.
Anybody in the room?
Can you hear me?
Yes.
Yes.
Okay. I had a question. How would you tackle the problems of maybe cache coherency and so, because you said that two processes can be mapped to the same virtual block, but we only write back memory once it's evicted from the cache. So I think that could potentially create some cache coherency problems in case these two problems that are mapped to the same virtual block are running on two different cores.
Oh, two different cores. So in such a setting, if you, there are more details about that configuration in the paper, but to briefly answer your question, in such a setting, there would be one central memory translation layer for one. Basically, we choose one of the memory translation layers of one of the cores as the one that will coordinate the memory requests and takes care of the cache coherency and coherency related issues for all the memory accesses. So in case the processes are running on different cores, we'll make sure that that memory transition layer of one of these cores is actually taking care of maintaining the coherency. Does that answer your question?
Yeah, okay, thanks.
Yeah, of course.
Master, we have a question from YouTube. Two questions. So the first one is, what are the minimum requirements for the memory controller to support VBI? Can you use it out-of-the-shelf hardware for it?
Out-of-the-shelf what?
Hardware, like
hardware.
Yeah.
Okay. Yeah, so the way that we envision VBI is to basically firmware running on a simplified core. So when designing VBI, what we were trying to make sure was to minimize the requirements, exactly like you've noticed. A very good point. We were trying to make it as comparable to the designs that were out there before. So what we noticed is that the requirements, memory requirements for VBI are no more than other prior basically designs. That, for example, Pinnacle, that if you compare it to that, this is basically what we need. So as I said, you can think of it as a firmware running on a simplified core that is able to basically manage the tables that I mentioned that is the functionality that you require for memory transition layer. And a simplified course similar to many of the designs, prior designs, would be enough to implement that. I hope that answers your question.
Second question from YouTube, thank you, is, and a second question. In the virtual machine use case, how can you prevent the virtual machine from creating a virtual address space anyways, and then map it to VBI? Does they require specialized virtual memory support?
Sorry, I did not understand the question, Geraldo.
I also didn't understand that actually. So
Yeah.
in the virtual machine use case, how can you prevent the virtual machine from creating a virtual address space and then mapping to VBI? So I think inside the virtual machine itself, how can you prevent it from it to create another virtual address memory space? So is VBI should be applied? I guess the question is, can VBI be applied concurrently, right? Not concurrently, recursively, also inside the virtual memory address space, right? Inside the virtual machine.
So it is not possible to basically implement VBI recursively. I can, if that is the question, I can understand where it comes from. Maybe because the default is that the memory management that happens in the host is basically replicated in the virtual machine, because virtual machine is not aware that it is running on a host. But in the case of VBI, what is different is that the memory management is the address translation and memory allocation part of the memory management is unified, and it happens only in a single point in the system, right? So when we apply VBI to a system, when VBI is enabled in a system, there's one single point that is responsible for memory allocation and address translation. So it's basically impossible to allocate a virtual block without that single point in the system, which is memory translation layer, being aware of that. So the way that it works is that every time that you do a malloc, that malloc is basically creating a virtual block. There's more detail, of course, into it, which is explained in the paper, but you can think of it that as the process requests for a virtual block of a specific size, and then after that, it can use malloc, a specialized malloc, to basically allocate data within that virtual block. So there is no virtual address space anymore per se, but we're basically dealing with virtual blocks instead. And the virtual address space of a process is the collection of the virtual blocks that are attached to it. So I hope that answers the question. And I hope that I understood the question correctly. So while we're waiting for more questions, hopefully, I just wanted to say that there are some follow-up directions, not necessarily directions, but projects, let's say, after VBI that look into other aspects of virtual memory challenges. You can find more information about those on Safari's website. And in case you're interested, you can contact us to basically discuss things further in case you guys are interested or have any comments or ideas.
I think there's one last question on Zoom, which says, how realistic is it that new processors will change to this new system?
How realistic is it? It's
what are the adoption issues, I think?
Oh, okay. So I would say the most important one is the hardware requirements for VBI, right? And in terms of enabling VBI, the first step would be providing the hardware requirements in the memory controller. And assuming that that is available, basically the way that the application needs to change is the way that we envision it is that a compiler pass can identify the mallocs and basically attach a virtual block request prior to the malloc, basically insert it prior to the malloc, so that request for virtual block is happening before the malloc, which is the way that virtual block is working, and then translate the malloc into the malloc version that virtual block uses, which is basically it requires the ID of the virtual block that malloc is going to happen in. So that's on the program side, which this is as much change as we need on the program side. And then in between, everything would be transparent to the program. Memory management would be completely transparent to the programmer. I hope that answers the question.
Thanks, Nasser. We have two more questions from the classroom here. So the first one is, how does the virtual address fragmentation looks like? When multiple processes complete for the same block, would it lead to high fragmentation? So it's basically a question related to fragmentation.
Okay. Yeah, that's a great question. So the way that VBI works, actually, one of the benefits of VBI is that when memory allocation is required by a process, what happens is that VBI actually looks at the current state of the physical memory and the available contiguous regions of physical memory, if any. And if there's no such, if there's not large enough contiguous physical memory region, it looks for smaller regions. And all of that happens in the granularity of the class sizes that I showed you earlier. In this paper, we look at 8 different size classes, size classes. So we basically look for the, what happens is that we look for the smallest size class that can fit the data. And then VBI memory transition layer starts looking for a contiguous region of physical memory that can fit that virtual block. And if that's not available, it basically breaks that virtual block into the next smaller size class and then starts looking for contiguous regions of physical memory that are of that new virtual block size. It goes all the way down to the smaller size classes to basically find a region that it can fit in. And we have different mechanisms to basically not always allocate the entire requested amount of memory and just allocate the smaller virtual blocks that are required and necessary now to basically lower the overheads of memory allocation and memory accesses. And that is explained in full detail in the paper. But in terms of fragmentation, yes, it is possible, like regular systems. And what we do is that, similar to the conventional systems, VBI would be able to basically monitor the current state of physical memory and do, basically you can implement any fragmentation solution that is available in current systems in VBI, and you have the option of implementing that inside the memory controller, running on the simplified core that I mentioned to basically implement any of those techniques similar to garbage collection. These techniques can implement their parallel to the Vbi design, and they can be implemented on top of VBI. Yeah. Does that answer the question?
Yeah, hopefully. I think we should get moving. I think if people are interested, they can contact Nastran.
So, Onur, we have 2 more questions here from the.
Okay, wow. Okay, I guess let's ask them also, since
okay,
we may need to end a little bit later, given that Ataberk is going to present. But let's go ahead.
Okay, so I'm going to ask them out of order because of some buffering that I'm applying here. But the first one is, how much do existing programs need to adapt to this memory system? Are there many situations where programs are relying on a traditional memory system, or did the programs in the benchmark just work? So this is what should change in the system.
So great question. So if you there's more details in the paper, but if you look at the paper, we have some instructions, special instructions that the programmer needs to use basically to notify virtual block of any request for a new virtual block or releasing a virtual block, not needing it anymore. Right, so these are the kind of requests that the programmer needs to include in the code prior to, let's say, malloc, or where there is the allocation, right? So as I said, in our case, what we did was that we we basically just needed to insert a virtual memory request, a request for a new virtual block, a virtual block request prior to a malloc, and then when there was a deallocation, we would basically detach that virtual block from the process. But the back end happens transparently to the program. So the changes that the program needs to be aware of, or basically what programmer needs to do, goes as far as just adding the new request for a new virtual block, or releasing a virtual block, or resizing a virtual block in case the data grows more than what it initially was thought of. So yeah, this is, I actually have an example of piece of code, small piece of code as to how malloc changes into, needs to change, and what instructions need to be added before a malloc for VBI to understand what's happening and what are the requests from the programmer. But yeah, and then in our case, basically it was equal to a compiler pass that identifies the mallocs and just adds the VBI virtual block requests.
Sarah?
Mhm.
The second question is, did I understand correctly that more than one process can be mapped to the same virtual block? And if so, what are the use cases for that functionality?
Oh yeah, so that's a great question. Yes, a virtual block can be shared between, not let's say shared, but necessarily, but different processes can attach to the same virtual block. And the use case is that when you actually need to share data, right? Instead of, so what happens in the conventional system is that data in the physical memory is one region of physical memory, and then different processes use different virtual addresses to actually map, use different virtual address spaces, regions, to map their address space to that physical region of physical memory. So we would have two virtual address spaces, one for each process, that map to the same physical address space, right? That basically that data is stored in. But in VBI, what happens is that because the virtual addresses are unified system-wide, there's one region of virtual VBI address space, which is one virtual block that is mapped to that physical address space, right? So as you can think of it, that data, which this virtual block points to, can be shared between different processes. And it's just, it happens differently compared to the conventional virtual memory, because now they're just pointing to the same virtual block to actually access that physical memory. And the use case of that can be just regular sharing, or let's say libraries that different processes need to use. The code section can be shared between different processes, and basically any kind of sharing that processes need to do. Yeah.
Sarah,
Mm-hmm.
if there is any other question. There is no other question. Thanks so much for the talk, Nasser.
Of course. Yeah, thank you for listening.
Yeah, thank you, Nastran. I will mention to people that this is a really good area of research for sure. As I mentioned in an earlier lecture, it's good to rethink virtual memory given the current trends, and this is a paper that takes a bold approach toward that direction. If you're interested, feel free to read the paper, but there's a lot more to do in this area, as Nastran also mentioned. So hopefully some of you will be interested in let's say, figuring out how to really get the benefits of virtual memory without the downsides of traditional conventional frameworks that we have today going into the future. Okay, with that, I think we can move to Ataberk. So Ataberk is also a PhD student. He's a beginning PhD student in the group, but he's been with Safari for a few years now. He's been an intern, and he did his master's thesis together with us also. He's going to present two works that are going to have a similar flavor, but they're not going to change the virtual memory system as much, but they're going to add more information so that we can communicate semantic information from the applications and the systems down to the hardware better. One work is Nandita's work. Ataberk actually wasn't involved with it, but he learned a lot about it by implementing it later on a real FPGA system. Nandita was a PhD student in my group. She's right now an assistant professor at the University of Toronto. It's easier for Ataberk to present it because Nandita has a lot of lectures to present at Toronto. But I think Ataberk is quite an expert in this area. The second work he's going to present is going to be on MetaSys, which is an implementation of this system on an FPGA, and it's an open source implementation. So you can ask him a lot of questions. And we're likely going to overflow the time due to these technical issues. So if you really need to go somewhere at the end, don't feel obliged to stay. This is all optional material, as you know, for your benefit. And who knows, maybe you'll invent something based on what you see here. So Ataberk, please take over.
Okay, thank you, Onur, for the introduction. So as Onur mentioned, I'm going to present this paper today and another work afterwards. So this one is a case for richer cross-layer abstractions, bridging the semantic gap with expressive memory. It was published on ISCA 2018. Nandita was the lead author for this project. And I will probably refer to this as XMEM. That's the short form we use to refer to this work. It's short for expressive memory. So I'll begin. So when we look at how we compute today, we have different types of software, and these are running on multiple modules that form the hardware. Basically, the computer is also made up of different modules now. We have memory, we have GPUs, we have specialized accelerators and CPUs. And the interface between these two layers are defined today typically by ISAs, or instruction set architectures, and virtual memory. And this enables expressing functionality through, from software to the hardware. It's specialized on doing that exactly. But it's unclear how this cannot be used to do performance optimization. So there's metadata that would be otherwise useful for performance optimizations. We cannot really fit that metadata through this thin gap here. And therefore, software optimizations need to work in their own layer, and then hardware optimizations have to work similarly in their own layer. So I'll talk about some of the higher level information that's not available to the hardware. On the software side, we have data structures, the organization of data structures. If we have a tree, if we have a database or a 3D array, for example, code optimizations, and access patterns, and data types. So these have to all squeeze in through this very thin interface, and then they will be output as ones and zeros, and that's the only thing the hardware can observe right now. And this is in form of these binary digits, in form of instructions, and communicated in form of instructions and memory addresses. So this is what the interface looks like today. It allows us to express functionality very well, but we cannot express metadata that would be useful for performance optimizations and other optimizations potentially. And the work XMEM targets this interface. It tries to widen this interface so that we can transfer higher level information, program semantics, and basically enable hardware to look at software level information to perform optimization. So this is the outline for this talk. I will start by motivating why we need a richer cross-layer abstraction. So I'll try to motivate it over first performance optimization that's typically done in hardware. So we design hardware to infer and predict program behavior to optimize performance. In caches, we have different replacement policies. We have prefetchers in our processors that try to predict the access patterns of programs, and then fetch prematurely the data that will eventually be accessed, hopefully, by the program. And in memory controllers, we again try to predict which rows, for example, will be accessed in DRAM, so that we can enable that row beforehand, and then we can improve the latencies, the latency of accessing memory. But this is, again, these are all done by these components by looking at the instructions and memory addresses, so there's binary digits. So with a richer abstraction, we state that software can provide more information, and this can significantly help hardware. So we had seen these before. So if we convey the data structures, the information about data structures, the way they organize the basically organizations they represent, like a tree, the pointers they have to different nodes, the access patterns of, for example, a graph workload, which nodes are going to be accessed likely after this node, or data types and layouts of these data. So is this an array, or is this potentially a floating point number that I could approximate? And if we actually convey this information, you can potentially think that data structures and access patterns will be helpful in performing some data placement, such that we can access this data much faster, or we could use this information to better prefetch, or more accurately, or with lower overhead, basically prefetch the same amount. Or we can use the data type information about data types to perform compression. So if we know that this data type is compressible, we can easily make that decision to compress it in hardware. And again, so by expressing all this information, we can enable these different optimizations that we list here. So for cache management, data structures and access semantics make sense. Again, a working set of the program makes sense to use. Data placement in DRAM, similarly, access frequency, use working set. These are all information critical for these hardware optimizations. And if we expose these informations to the hardware, the hardware can make these decisions much more efficiently. About the software side, so it's not only hardware that we will help if we expose this information, but also help software level performance optimizations in a different way. So I'll try to describe that. So we use platform-specific optimizations to tune software today, and this will become more clear. One example is cache optimization. So we have a program, and the program could be some scientific workload kernel accessing some array in a specific access pattern. So what we do is we tune the working set of this program, meaning that we tune it such that the working set of this program, the addresses touched by this program in one point in time, will fit in our X megabyte cache. And to do this, we clearly need to make modifications in software. And to do this for another program, we need to repeat the same step again. And also we need to repeat the same step if we have a differently sized cache for another platform. So here, software optimizations make assumptions regarding hardware resources, and also we need to make these assumptions, we need to reperform these optimizations for every different type of hardware. And this brings significant portability and programmability challenges. And with a richer interface, what we can do is we can actually take this burden on software and bring it to hardware. So one example would be stealth for this cache optimization. Instead of specifically tuning the working set to a cache, to a specific cache, what we do is we convey this information. We convey the working set, the size of the working set, and we use information to hardware. And hardware in this case could be the cache. And therefore we express only program information. So we don't have to tune our code again for a different hardware. And the system itself, in this case, maybe the cache, handles optimizing for specific details like the cache size, the memory organization, if there's a non-uniform memory access. The software doesn't have to deal with these anymore, and we have therefore greatly improved the portability or the programmability of the code. So in this work, we specifically, the authors specifically explored on the hardware side performance improvements and performance optimization on software side programmability and portability optimizations, but you could probably think of more. And there are prior work that conveyed this information. So it conveyed higher level program information to hardware in a way to build hardware software co-design systems. These were in the form of cache hints, prefetcher hints, or annotations or new instructions. But the problem with these works is basically they're not easy to scale. So it's not really acceptable at some point to add a new instruction for each new optimization that we want to perform. And these are also not portable because they make assumptions about the underlying resources like the cache optimization example did. And these are the significant downsides that limit adoption of these systems, of these hardware software co-designs. And our goal, or the author's goal in this paper, was to design a rich, general and unifying abstraction between hardware and software primarily for performance. Okay, so I'll move on to the design of the expressive memory. So we have 4 key design goals in building, in developing XMEM. So it should be supplemental and it should be based on hints only. This means that it should not affect the functionality of the system or the correctness of the system. It should only provide supplementary info. And this way, we don't need precise hints, and the system implementation can be simpler, basically. Also, anything we put on the, basically any module we add to the system to realize this hardware software co-design doesn't necessarily have to be on the critical path this way, because we can ignore all of these extra information being transferred all over the place. It should be general, and it should be general enough to express program semantics. These are different program semantic information that's useful in different optimizations, and it should be general to be able to express all of that, hopefully. And it should be extensible to support more semantics. And the abstractions we provide should be based on application characteristics and not on system-specific parameters. And this is important for portability, as the programmer doesn't need to know about the hardware details. And finally, it has to be low. It has to incur low storage and performance overheads, and also it shouldn't really affect the correctness and functionality of existing interfaces. So it should be compatible with the existing interfaces like the ISA and the virtual memory. And here's an overview of expressive memory that satisfies these key goals. So if you look here on the application side, we have an user interface, application interface from expressive memory. And to the system side, we have the system interface. And expressive memory in itself is a system that summarizes and saves program information. So we have 2 key challenges in developing this interface. The first one is it should be general and it should be high level, and this will allow us to convey all this information that we talked about, like data structures, data types, access patterns. But at the same time, we have to express these details to the hardware, and they have to be architecture specific and low level. This has to be low level information, like what to prefetch, which data to cache. And the key here is basically all this information that we supply from the software side doesn't need to necessarily be used to perform all these operations. So we have to do some summarization basically of that data. And the second challenge is we have to track these properties that continuously change with low overhead throughout the running of, throughout the execution of a program. So again, program behavior keeps changing as it's being executed, and data structures are accessed differently in different phases. Sometimes new data structures are allocated, and we need a dynamic interface that continually tracks program behavior. So we want to convey lots of information using this interface, and you could potentially see that this has a chance of becoming very high storage and communication overhead, incurring storage and communication overhead basically, and it's important that we don't do that. By don't do that, I mean this system should not incur high overhead when it's trying to convey lots of information, but not to convey lots of information. So for this, to deal with these two key challenges, we developed this new hardware-software abstraction. Here we have on the software side an application. This application has many different memory regions. And finally, we have the system on the hardware side. What we do is we associate memory regions with what we call atoms. And we will take a closer look in the next slide. So we will associate every memory region this application has with every fixed size, let's say, memory region with an atom. So we will take a closer look. It is to define its a hardware-software abstraction to convey program semantics. And it looks like this. Basically, it has some program attributes, mapping information, and state. So mapping is essentially describing which memory region this atom is mapped to. So is it like a tree, a whole tree, or a node of the tree? This mapping component will tell us that, or will keep track of that. The program attributes are all this metadata that we've talked about previously. Data properties like if it's an integer, if it's a floating point character, if this is compressible or approximable. Access properties like if this has enough, or like access rights, for example, if it can be read to or read or written to. Access patterns and access intensity, like how frequently am I accessing the structure. Data locality, the working set of this, the memory region that this atom is mapped to, and how frequently it's used, and potentially many more semantics. And also at the atom holds a state, which indicates if it's active at that point, or valid or invalid, basically, meaning that this atom should be considered by the system as conveying correct metadata. So if it's invalid, it's not, we discard this atom. And it has a unique ID for itself. We define 3 operations to manipulate atoms. So the first one is create. By using create operations, we fill up all these program attributes the atom has. By using map and unmap operations, we map this atom to different, we can map this atom to different memory regions and unmap it from places that has been mapped already. And we can use activate and deactivate operations to manipulate its state. So here's an example on how we use atoms to express program semantics. So first we have this memory region that we allocate using malloc. And then this could be, in this example, it's a 3D array. And we create an atom specifying the data properties and access patterns and everything. And we call this atom 1, or it's the atom with ID 1, basically. And then we map this atom to this memory region and then activate it. And once we activate it, the system will know that this memory region is associated to this atom. Now, by design, these attributes cannot be changed on runtime. So if we want to change the, if we want to specify a change in semantic information for the same memory region, we have to map it to another atom that we have created before, not on runtime, basically. So for that, we create multiple atoms. And then to do that thing that I described, to switch the associated program semantics, we switch the mapping of the atoms. So we unmap atom 1 and then we map atom 2 to it in this case. So this is how we use atoms to express program semantics and expressive memory. So we implement these 3 operators in different program lifetimes, let's say. So compile time, we have the create operations working, and also in the load time, the create operations will take place. And on runtime, only map and activates take place. And this will become more clear. So in compile time, these create operations are basically recognized by the compiler. So we modify the compiler to understand that these are atom create, basically commands for it. And then it will basically accumulate this atom ID to program mappings itself. And then it will embed this in the object file or the executable file. So by doing this, we have avoided doing high overhead operations at runtime. So create operations, depending on the amount of semantic information you want to embed, could take a long time. But by doing this in compile time, we have essentially avoided it at the cost of it, at the cost of doing it in runtime. And in load time, what happens is, as the program is loaded into memory for execution, the OS will take a look at this atom segment in the object file or in the executable file that the compiler has put, and it will invoke the attribute translator to separate the attributes, the relevant attributes to their hardware modules. So this is what we were talking about back when we were saying how general interface kind of contradicts this low-level information. So here we made the user interface general, but we are also making sure that every component, the low-level components, retrieve only the information they need by invoking this attribute translator here. So this is addressing the first challenge. And yeah, so this is architecture agnostic and it's general, and this low-level side is architecture specific. And here's how maps and activates. So maps and activates take place during runtime. As I said, we implement new instructions in the instruction set architecture to support this functionality. And the design, we have one design challenge. So how do we do this with low overhead? So we want to change the mapping of an atom, meaning that we will do some memory operations potentially. So here's, before we describe how we do it in a low overhead, maybe another look at the same figure. We have, to implement this, basically we have 2 structures. We have the atom address mapping table and atom status table. So here you can see that the atom address map is indexed by the memory address and it stores the atom ID. So the system, to retrieve semantic information, it will have to access this table. And the way we change the mappings for atoms is basically we fill basically the relevant portion of this table with the correct atom ID. So if I want to map atom ID 0 to the memory address 0, I will be filling 0. I will be filling here with 0. And if I want to unmap it at some point, I will remove it, and then I will map something else in its place. And this atom address map is stored in memory. An atom status table is similarly indicating the validity of the atom. So we implement instructions, like we implement 2 instructions, map and activate, and their counterparts unmap and deactivate. So activate and map instructions we use to manipulate these 2 tables. The reason why we keep atom address map in memory is because it's a large structure compared to the atom status table, which is indexed by atom ID, which are relatively smaller in numbers compared to memory addresses. So we can manage the atom status table in an on-chip structure, but the atom address map goes to memory basically. And for each component in the system, we have a private attribute table. Each component that will make use of these this metadata to perform optimizations has this attribute table, private attribute table that the translation component in the previous slide fills when we execute the program. So this table will hold per atom ID the attributes that it needs to perform a specific optimization. So again, to remind you, we want a low overhead system, and one thing that helps us achieve that is that this has no impact on functionality. So these operations that we support, or these optimizations that will be done, the performance optimizations are not really affecting the functionality of the system. So this means that these structures don't have to be in the critical path of the program, of the execution. So we can heavily optimize for low overhead, meaning that the structures can take longer to access if we're optimizing for low storage overhead, for example. Here's an example of how these structures are accessed by a program. So this is a random program that's doing matrix multiplication here. And on a last level cache miss, we have on the hardware side the L3 cache and a prefetcher that works with the L3 cache. They will send this memory, the memory address of the missing request to Expresso memory system, and they will retrieve an atom in return, atom ID in return. And Expresso memory system, what it will do is it will access this atom address map table that I showed you in the previous slide, and find the atom ID for that memory address, and then return those atom IDs to the clients or the requester hardware, basically. And they will access their own private attribute tables to retrieve information relevant to them. So in this L3's case, it's going to be the reuse characteristics of the workload and also the tile size. And for the prefetcher, it could be the access pattern. Yeah, this, I will come to these next. So, and now I will talk about the evaluation of this paper. And in this paper, the authors evaluate two use cases. One of them is more specific, more focused on the first one, is cache management, and it's targeting portability as a software optimization. And the other one is doing data placement in DRAM, and this targets performance. So I will talk about this first use case only. And it's improving portability of software cache optimizations. And here we're trying to we're working on this cache optimization that tries to fit the working set of the program in the cache. And these are example workloads that make use of this optimization, basically. And here's a pictorial, perhaps, example. We have this computation that we want to do. It could be dot product or matrix multiplication. We want to multiplying array A and B to get C. And this is an extremely large array, for example. What we want to do is, if we're going to access multiple times these portions of these arrays, we want to keep them in the cache and access them as much as we can before we evict them and bring in other parts of the cache, of the array to the cache. So this is what tiling is trying to deal with. So we're trying to, we're splitting this array into tiles, and then those tiles, we expect them to fit into our caches nicely. Okay, so here is the description, is the system configuration that the authors use to test their use case. And you can see the same in the paper as well. So I'm not going to go into detail this evaluation. Okay, so the authors have, or we say that basically correctly sizing the working set is critical in this tiling use case. So here's a plot showing the execution time for a workload on the y-axis and the tile size that was used to configure or tune the program on the x-axis you see in kilobytes. It's for generalized matrix multiplication workload. And here is basically what we see when we tune it for different tile sizes, right? Here until some point in the beginning, we see that the bigger tiles we use, the better performance we get from more reuse. But after some size, after some tile size, we start to trash the cache, meaning that we evict useful cache blocks. And this introduces a performance overhead, and this keeps increasing as the tile size increases. And optimal tile size depends on the available cache space, not just the whole, the size of the whole cache. And this is basically the root of portability and programmability challenges in software tuning-based software optimizations. So imagine we tuned this, assuming we had a tile size of 6 kilobytes. It would work well in one system, but it will probably not work well in another system. We're trying to solve this issue using what XMEM provides us. So what we do is we, instead of tuning it, tuning the program for tile size, just doing that, we do that plus we map an atom to a tile, and we specify that it has high reuse and also the size of the tile, basically. And what XMEM enabled memory component, hardware components do is, if the tile size is less than the available cache space, meaning that there is enough space for us to bring this whole tile in, it will apply the default policy. In this case, this hardware module is, you can imagine to be the cache controller or the cache itself. So we apply the default policy because we don't expect cache trashing to occur. But if the tile size is larger than the available cache space, what we do is we pin, meaning that we keep forcefully keep one part of this tile in the cache. We don't let it be evicted. And instead of trying to fetch the remaining parts of this tile by using load operations or read operations, we just try to prefetch the rest. So by prefetching it, we avoid trashing of the cache block, of the useful cache blocks, basically. So in doing so, what we've done is we've let the software express some program level semantic information, and then the hardware used this to optimize for performance. Okay, so here is again the same plot, but now we will see that XMEM improved this trashing overhead. So this trashing problem by reducing the execution time by 47%, where the baseline system performs the worst. So the conclusion from here is that knowledge of locality or the locality semantics enables more intelligent cache management, and it improves programmability and portability, because now maybe the software developer doesn't need to worry about that much how he needs to or she needs to tune this specific program to different cache sizes. And here are some results across more workloads. You can see that XMEM behaves similarly for all these different workloads that use tiling, and it helps keep the performance overheads to very low, or it improves the performance. So there's more you can see in the paper. The second use case is basically leveraging data structure semantics to enable more intelligent OS-based page placement in DRAM, and more details about the implementation, some more overhead analysis, and there's like a discussion of other use cases of XMAP. And to conclude, there's a narrow interface between software and hardware, and this does not allow too much information to flow today. And this interface is defined by ISAs and virtual memory. What expressive memory does it widens this interface and allows higher level information to flow between the two layers. And it implements a general and architecture agnostic interface to the software. And doing so, it provides key information to aid system components and optimization, basically. So I'm done with the XMAP part of the presentation. If you have any questions, I can take them now. Should I continue with the rest?
So let's see if there are questions. But I think it makes sense for you to complete, even if people are not there, for example. Are there questions in the room or on Zoom or YouTube?
Not have question here in the room.
Okay.
We'll continue.
Yeah, unfortunately, the technical issues delayed you to start.
That's fine.
But as I mentioned, I think people can feel free to drop off. I think Ataberk has, I don't know how much more time you will take. As long as we have the room, I think we should just continue.
10, 15 minutes, maybe.
Okay, that sounds good. And I will mention that I think this paper was published at ISCA in 2018, and Ataberk has a link to the paper over here. It'd be good to put these links on the course website also.
Yeah.
I think Geraldo can do it. And this is certainly this is one of the few works that try to communicate semantic information in a general way from the software to the hardware. And there's actually a companion paper to this. I don't know if Ataberk has a link to that, but it's called the Locality Descriptor. And the idea is to have a specific expressive memory system in GPUs where you can communicate the locality information of different data structures in a GPU so that you can exploit that for various purposes like thread scheduling, data mapping, non-uniform memory access, data mapping in a GPU. And Nandita is also is the first author for that work. And we did that work together with NVIDIA. And that shows you that the idea is applicable to the specific case of locality exploitation on GPUs. And it actually leads to quite significant benefits in terms of performance if you can express the locality characteristics of data structures separately and do optimizations based on them. So I'd recommend people to actually look at that paper as well if they're interested in this topic. So Geraldo, it'd be good if you can link these from the seminar website. If there are no questions, then we can continue.
Okay. I'm just checking Zoom chat. Okay. So the second paper I will present is named MetaSys, a practical open source metadata management system to implement and evaluate cross-layer optimizations. And this was recently published on TACOD 2022. And there's a link to the paper as well here, but you won't be able to click it now. And this was also led by Nandita. And as Onur mentioned in the beginning, I am an author in this work. So yeah, I'll start with an executive summary. So we have seen that hardware-software cooperative mechanisms are important to enable performance optimizations. And the problem is that these techniques are hard to implement because they require changes across the whole stack, whole computing stack. And existing open source infrastructures for implementing these are not designed to facilitate the implementation of new techniques. Sorry, somehow we went to the end. Sorry. Pressed the wrong button. Okay, back to the correct place. So, yeah, as I said, these are not these techniques, existing techniques, are not facilitating the implementation of new cross-layer techniques, and they're not providing these three features that MetaSys provides. So the first one is they don't have a rich dynamic hardware-software interfaces. They don't enable low overhead metadata management, and they don't have interfaces, for example, to key hardware components. And the key idea for this work is to provide all of them at the same time. And our goal in this work is twofold. The first one is to develop an efficient and flexible framework to enable rapid implementation of new techniques and new cross-layer techniques. And we want to also perform a detailed limit study to quantify the overheads associated with general metadata systems. So I will, since I've talked about XMAP a lot, and this is you can think of this as a continuation of the project. It's an implementation for XMAP essentially. I will describe the key structures we have here immediately, and I will try to relate them to what I talked about in the XMAP part. So we have what's called an optimization client. This is the hardware module that will access metadata to or access program information to perform an optimization. So it accesses this what we call metadata lookup unit or atom lookup unit. Whenever you see a metadata in this part of the presentation, you can immediately think of atoms in XMAP. So it's an atom lookup unit. It will it also contains a cache of atom mappings. So instead of always accessing memory to retrieve metadata mappings or atom mappings, we cache them in the structure. And the metadata lookup unit, if it cannot find the mapping in the cache, it will first need to translate this virtual address to physical address to access the metadata mapping table or atom address map that resides in main memory. Here, it's the same structure. It's indexed by the memory address and it holds the atom ID. And then this will be placed, this mapping, when it's found, it will be placed in the metadata mapping cache. And then using this, we will access the, using the atom ID, we will access the private attribute table to finally bring the optimization client its attributes. And we developed an Fpga prototype for this. So we prototyped it on Xilinx Z-board here that you see on the left. And it's the system is within a real RISC-V system called Rocket Chip. And Rocket Chip, a diagram of it you can see on the right. It's a simple system with interface to DRAM, some support for accelerator, or a coprocessor is a better fit here, and level 1 instruction and data caches. We implement two main components in Rocket Chip to support this flow that I described 2 slides ago. And the first one is what we call the atom controller, and it manages the attribute table. So it executes create and activate or deactivate instructions, and also performs atom mappings. So it will execute map and unmap instructions, and to do this, it will retrieve an atom ID based on physical addresses. And the metadata lookup unit, it responds to clients or hardware modules that do optimizations and provides them with atom attributes, and it also contains the metadata mapping cache. So here I described the changes we made to Rocket Chip. So this is an extremely simplified diagram of Rocket Chip, a tile, Rocket Chip's tile. It contains the core processor, TLB, and the L1 caches. So we put everything within the coprocessor because it's tightly integrated with the core, and it can easily fetch instructions from the program that we're executing. Maybe to remind you here that we implement similarly the create, map and unmap, deactivate, activate instructions to perform operations on atoms. So this is useful, and since the coprocessor is tightly interfaced, integrated with the core, we implement these structures over there. The user program interfaces with the atom controller here to modify the attribute table using instructions, as I mentioned, and the optimization client communicates with the metadata lookup unit over what we call a lookup interface, and this can convey attributes and addresses. Basically, this is a generalized interface for every optimization client to communicate with the metadata lookup unit. And we fully open sourced our implementation on GitHub, and you can access it using this link. I talk about now our evaluation methodology. So we run a set of workloads on our prototype Z-board to basically stress test the generalized general metadata management system. And here are the micro benchmarks and the programs we run. And this table lists the configuration of components in the system. So I will show you the key results we got from our analysis. So first, what you see here on the x-axis is all workloads we have run. And the y-axis is the normalized execution time for when we perform lookups based on every access, every load and store access, and every L1 miss. So miss only stands for every L1 miss, and all accesses stands for all requests basically coming out of the code. So what we're trying to do here is to stress the metadata management system implementation. And that's why this might not sound like an optimization use case, which it isn't so weird, but it is good for us to stress the basically the implementation. And these are normalized to the baseline system that runs these workloads without any metadata support. And on average, we see that this only the lookups only occurred low performance overhead, which is 2.7% on average for all accesses. So here's what we plot the metadata mapping cache hit rate. And you can see here, this is a similar plot. We have two bars, miss only and all access stand for the same thing. And we observe that metadata mapping cache can cover 81% of requests on average. So this changes with the access patterns of the workloads themselves. So for the micro benchmarks, you see that this random micro benchmark we created accesses memory randomly, and therefore it has almost no hit rate on the MMC. Similar workloads with similar behavior will also have similar hit rates. And you can also see the correlation between L1 data cache hit rate and MMC hit rate by looking at these two plots, two bars for these workloads. Since we're only triggering MMC accesses on L1 misses here, we see that there's a great difference for this 3D array workload. And we look at the impact of tagging granularity. So this means that the tagging granularity indicates how large of a memory region each atom is mapped to. So 64 means that an atom is mapped to cover a 64-byte region in memory. Similarly, 4K, and then in typical systems, 4K is the size of a page. So here you can imagine that an atom covers a page basically. And we inspect the impact of this on performance similarly. And we have different tagging granularities on different bars, and the X and Y axes are the same. And we see that performance impact increases with finer granularity support. So if you want to support a tagging granularity of 64 bytes, we have to suffer from this higher overhead. And the final result I want to show you is the effect of contention. So we, again, evaluate our prototype using this time 2 different implementations. So in one client implementation, we have we feed the metadata management system with all memory requests originating from the Rocket core. And in the 2 clients, we have the same request coming to the metadata management system, plus every memory request the page table walker needs to complete also goes to the metadata management system to perform a lookup. And we see that in multiple clients don't significantly affect performance. So it's, we observe that only 0.3% overhead on average. And this is suggesting that the system is scalable. Okay, so I'm done with the MetaSys part also. I think I can take your questions now if you have any. And thank you for also listening to my presentation and actually going over 20 minutes over time.
Okay, I assume there are no questions in the room. Geraldo, is that correct?
Yes, there is no question in the room, and there is no question on YouTube also. So thanks a lot for presenting, Ataberk.
Yeah, thanks, Ataberk, for presenting. And if people are interested, they can certainly look at the paper. And this is completely open source, so feel free to play with the code and implement whatever semantic information you want to convey to a RISC-V core and test the system. Right, Ataberk?
Yes, we would appreciate that effort.
Yeah, and if people are interested in, like, if you can certainly contact us if you're interested in doing that, and if you have any issues with the open source code.
Yes.
Okay, if we don't have any other questions, then we should not continue. We should not delay things further. Thanks, Ataberk and Nasjan, for presenting. So next week we're going to start with the student presentations. Right, Mohammed? Maybe you can take over and conclude.
Yeah, I think so. We will start next week with the presentation. There will be a short quiz after each presentation. So we'll have 2 short quizzes next week. We will send you further instructions over Moodle. Thank you so much, everyone. Nasran, Ataberk, and see you next week.
Thank you. Goodbye.